Here's the solutions for Chapter 6 area approximation practice. The first set of questions are about this function from 0 to 3. So I'm just going to make a sketch of that we can refer to. So from 0 to 3, just a parabola, so it looks something like this. First, we want to find a right Riemann sum using 3 equal subintervals. So the intervals are just from 0 to 1, 1 to 2, 2 to 3. And the right side, or the right edge of those, will give us these heights. Right, that's what it means to do a right Riemann sum. We use the right edge of each subinterval to find the height of the function. So those areas, that's going to be a 1 by 1 plus a, they're all 1 wide on the bottom, by 2 squared, and 1 by 3 squared. So 1 plus, so that's 14. The left Riemann sum will be using these. So now I'll have this rectangle, this one, and this one. And you might notice that the two of the rectangles are the same, right? So I have a 1 by 0 rectangle plus the 1 by 1 plus the 1 by 4, right? These are actually the same rectangles. We just got them because on one side it was the right and on the other it was the left boundary. So that's 5. Those are pretty lousy approximations, right? Not very close to each other at all. Midpoint, maybe you would get a little bit better approximation. So here we're going to take the height of the function at each of the midpoints. So that's going to be a 1 by, let's see, so the midpoint between 0 and 1 is 1/2 squared, gives me the function value, plus 1 by, this would be 1.5 squared is 2.25, or 9/4 if you want to leave it as a fraction. And then 1 by, this would be 2.5 or 5/2, so that's 25/4. Let me square that, so that gives me 1 plus 9 is 10, 35/4. Right? Or, what is that, 8.75? Trapezoidal sum, so the trapezoids, each one has a base of 1, so do that base divided by 2, and then add the heights on either side, the function value. So that would be 0 and 1 for this one. And then for this one it would be 1 and 4. And then for this one it would be 4 and 9. And that, let's see, we get 1, so 6 plus 13 is 19/2, or 9.5. And then using a limit, write an expression that represents the exact area. The exact area would be the limit as we squeeze the width of the rectangles down to 0 of the sum of the areas of all the rectangles. So those are all the x's squared. So you could notate it, this is one way to notate it. In each one of the little intervals, you pick an x, and then you multiply by the width of that interval, and you sum that over all of the i's, over all those intervals. That's one way to write that. And that would be equal to this. Right? You can see there's the x squared, and this is like the dx. Right? Based on those answers, what do you think the exact area might be? I mean, it's for you to just guess at this point what that might be. But let's see, the actual area would be it's 9. So you could have guessed these were the best approximations. Happens to be right smack in between those. Oh no, that's not true, is it? 9.5 would be in between those, so it's pretty close, but that's the exact area. You'll know how to do that soon. Number 2. So same thing now, we have the function e to the x. So I'll make a quick sketch of that from -1. This goes up in a hurry, so by the time I get to e to the 4th, that's a pretty big number, so this will not be to scale. So I have something small, e to the 0 is 1, then that's e, and then they get bigger in a hurry, so something like this. And I know this would be e to the -1, this is e to the 0 or 1, this is e to the 1, e squared, e cubed, e to the 4th. So the right Riemann sum, that would be using each of these values. Again, like number 1, each rectangle is 1 wide. So the heights, this is e to the -1, this is 1, e squared, e cubed, e to the 4th. So this will be these 5 rectangles. I'm going to use the right-hand edges, so that's the one that won't get used to make those rectangles. So it's 1 by 1, 1 by e, 1 by e squared, 1 by e cubed, 1 by e to the 4th. And we can get an approximation for that, the calculator real quick. So 1 plus e squared plus e cubed plus e to the 4th. So that's about 85 point. I'm going to get in the habit of rounding things to 3 decimal places. That's what the College Board likes us to do. The left Riemann sum, now we just use the left one, so that will be e to the -1, 1, e squared, and e cubed, and they're all 1 wide. So I have 1 by e to the -1, plus 1 by 1, plus 1 by e, plus 1 by e squared, plus 1 by e cubed. And if you notice in the calculator, you can fix that easily. You have all the right ones here, except for this one should just be to the -1, right, instead of, and then that will all line up. We have there, so that's about 31.561. Midpoints. So let's see, that means I have to do each of these. So that's going to be still 1 wide, 1 by e to the -0.5 plus 1 by e to the 0.5 plus 1 by e to the 1.5 plus 1 by e to the 2.5 plus 1 by, a little bit tedious. Is that the right number of them? 1, 2, 3, 4, 5. That looks good. So then, again, just have to power that into your calculator. So I have e to the -0.5 plus e to the +0.5 plus e to the 1.5 plus e to the 2.5 plus e to the 3.5. So that's 52. We'd expect it to be in between those, right? 52.035. All right. Trapezoidal sum. So now each trapezoid is 1 wide, so that's going to be 1 or 2. The first trapezoid has the right-hand edge is e to the -1, the left-hand edge is 1. Next trapezoid. Next trapezoid. Next trapezoid. And last trapezoid. There should be 5 of them, right? 1, 2, 3, 4, 5. And notice that the 1/2, just for calculator entry, to clean it up as much as possible, I have 1/2 on the outside, and then, oops, no, 1/5. 1/2 times and then all the stuff on the inside. So I have e to the -1 plus, and then I have 2 of those, so that's 2 1s or 2, plus then I've got 2 e's. I've got 2 e squareds, 2 e cubeds, and then only 1 e to the 4th. So notice the very first one and the last one, they only show up as one edge of one trapezoid, and everything in the middle shows up as both a left and a right edge. That's why those 2's are all there in the middle. So last, e to the 4th. And that should give, we would think it would give something closer to this, right, if we had to guess. And it does. So that's 58.676. And then using a limit, we could say that this is the limit as the width of the rectangles goes to 0 of the sum of all of the e to the x sub I in each one of those little intervals, delta x sub I. Right, something like that. Okay. The next sheet, next page, other side. I'm going to do this for the sine function now with 6 equal subintervals. Those are nice subintervals for the sine function, right? Because it means we'll be dealing with nice angles. So this would be pi over 2, this would be pi, pi over 6, pi over 3, 2 pi over 3, and 5 pi over 6, right? That's 1 pi over 6, 2 pi over 6, 3 pi over 6, 4 pi over 6, 5 pi over 6, and 6 pi over 6. And that's nice because I know the values of all those. I suppose you could just enter them in your calculator, but I know that this is 1/2. This is the square root of 3 over 2. This is 1. This is the square root of 3 over 2. This is 1/2, and of course that's 0. Okay? So with that in mind, if I'm going to do the right Riemann sum, that's each one of these is pi over 6 wide now. The first one is this high, then this high, and so those heights, right? This 1, 2, 3, 4, 5, 6. So let's see. It's pi over 6 wide, and then each one of the rectangles, that's going to be the same for all of them, so this time I'm going to factor that out. And then the heights are 1/2, plus square root of 3 over 2, plus 1, plus the square root of 3 over 2, plus 1/2, plus 0. Right, the last rectangle's height would be just 0. And that, let's see, pi over 6 times, I got 1/2 and a 1/2. I've got square root of 3, and another 1 there. That's 1.954. And if you notice the left-hand one, it actually comes out to be the same as this. When you do the left-hand endpoints, it's 0, 1/2, square root of 3 over 2, 1, square root of 3. So the 0 kind of moves to the other end, but that doesn't change the value. So again, it's this. That's because of the symmetry of this. Midpoints, I think we're going to need the calculator for that. So the midpoints, each rectangle will still be pi over 6 wide, but now the heights are going to be at these funky like pi over 12 values. So this will be at the sine of pi over 12 plus the sine of halfway in between, that's actually pi over 4, plus be 5 pi over 12, sine of 5 pi over 12, plus the sine of 7, it's odd pi's over 12, right? Plus the sine of 9 pi over 12 would be 3 pi over 4, plus the sine of 11 pi over 12. So 1, 2, 3, 4, 5, 6 rectangles, and make sure that I am in radian mode. I am. So pi over 6 times the sine of pi over 12 plus the sine of pi, oops, I didn't need to enter that there, did I? There, pi over 4 plus the sine of 5 pi over 12 plus the sine of 7 pi over 12 plus the sine, sine of 9 pi over 12, or 3 pi over 4, plus the sine of 11 pi over 12. All right, now that should be close to these values. Let's see. I mean, not terribly far away, right? So, good. That's our midpoint sum. 2.023. Okay, trapezoidal sum. Let's see. So trapezoids, each of them is pi over 6 wide, pi over 6 over 2, pi over 6 over 2. And then the edges of this trapezoid would be 0 and 1/2, and then 1/2, and the square root of 3 over 2, and then the square root of 3 over 2 plus 1, and then 1, and the square root of 3 over 2, and then the square root of 3 over 2, and 1/2, and last trapezoid 1/2 and 0. Right? 1, 2, 3, 4, 5, 6 trapezoids there. So pi over 6 over 2 is pi over 12. And then on the inside I've got the zeros, that's nothing. So I've got 2 of those, 2 of these, 2 of those, 2 of those again. Right, 2 halves of those is just a square root of 3, right? 2 of those, and the 0. And there's that. Oh, that's exactly the same as the first. That's interesting. So that's 1.954. And then using a limit, let's say that's the limit as the width of the rectangles goes to 0, the sum of the area of all the rectangles. And again, you can see how that resembles the integral sine x, and it's like the dx from 0 to pi. If you had to guess what the area, you might guess that it's 2. You would in fact be right, and that's what it is. That's in between those values. We'll prove that later on. Okay, so here's a table of values. We see situations like this a lot. Right Riemann sum using 6 subintervals. So that's rectangles, but they're not all the same width now. So I have a rectangle that is 1 wide by, this is the right edge of the first interval, is 4 high, plus 3 wide, and then I use the right-hand edge for the height, plus 2 wide, and the 3 will be the edge of that rectangle, and then 1 wide by, that's 0 height, that's a small rectangle, and then 4 is the height of that, and then this last one is 1 wide, and the right-hand value of the function is 2 there. So that's 4 plus 15 is 19, 25, 37, 39. You can check the math there. I think that's right. a left-hand Riemann sum using 3 subintervals. So 3 subintervals, we'd say here's 1, 2, 3, right? If the instructions aren't more specific, we just spread out as much as we can, as evenly as we can. So now I have an interval that here is, the first one is 4 wide, and I use the leftmost value. This one is 3 wide, and I use the leftmost value. And this one is 4 wide, and I use the leftmost value. So that's -4, 15. So these are obviously not, it seems like a pretty lousy approximation here. Midpoint Riemann sum using 3 subintervals. So the widths will be the same, right? The 4, the 3, and the 4. But now I'm going to use the midpoints. So the midpoint, now this one that was 4 wide will be 4 high. That's a big difference, right? This one that was 3 wide will now be 3 high. And this one that was 4 wide will be 4 high. So that's 16, and 16 is 32, plus 9 is 41. It's closer to that. And last, a trapezoidal sum using 6 subintervals. So the trapezoids, again, you have to pay attention to their different widths. This is 1 wide, so I'll put that over 2, and then -1 plus 4. The second one, sorry, is 3 wide, not 1. That's not automatically a 1/2, right? It's how wide it is divided by 2. 4 plus 5, plus this one is 2 wide. 5 plus 3. This one is 1 wide. 3 plus 0. This one is 3 wide. 0 plus 4. And this one is 1 wide. 4 plus 2. And you can add all that up. Let's see, that's 3 halves plus, that's 9 times 3, 27 halves plus 15 times 2, 30 halves plus 3 halves plus 12 halves plus 6 halves. I left everything as halves because then I can just add up the tops and then divide by 2. 2, 3, 4, 5, there's 6 of them as there should be. So it's 30, 60, 75, 81 over 2, or 40.5. That's pretty close to those. There.